So welcome to this unit three of mechanics of solids video. This one. So this is my third video in this chapter. Sorry, in this subject. So this is totally about flexural stresses. We are going to study about flexural stresses here. Before this, we have already studied about bending moment and shear stresses. So these are 2 marks questions which are 2 marks, but you can write 10 marks also for your knowledge update mention. I am doing these videos. So I have make some 9 to 10 important questions where you will understand in a better way. I hope. So this is totally about flexural stresses. Here I have made here total. So 14 questions are there. Stress, shear stress distribution also involving here. So let us start from the starting question here. So define flexural stresses. So what is this flexural stresses? Means the flexural stresses is the internal stress generated in a material. So the internal stresses developed in the material is known as this flexural stresses when it is subjected to bending. Especially bending comes here. So bending comes here. So when you are going to bend, some flexural stress is developed here. So this stress is studied here. So second question, if I am taking, so if I want to take this one, so here, if I am taking this is a beam, so this beam is bent here. So this beam is bent here. So after bending, what is happening? Their flexural stresses are developed here. Some flexural stresses are developed here. This is called as the flexural stress. Now, second question, coming to this second question, what is happening? So, second question, if you take one, define theory of simple bending. What is theory of simple bending? Already I have told you, the momentum forces are taken in order to bending, calculate the bending forces. So, theory of simple bending. So simply, if you bend and remove this body, it has to again regain its shape. If it is not regaining, then it is in the plastic state. If it is regaining, it is in the elastic state. So simple bending is we are going to apply all the materials with simple bending only, because if a length of a beam is subjected to a constant bending moment, so it's a constant bending moment is there and no shear force. Shear force should be zero. So then it is then the stresses will be set up in the length of the beam due to bending moment only. So then it is said to be a complete bending moment structure has been into this one, and that the length of the beam is said to be pure bending. So pure bending is only bending. You are going to bend a object. For example, if you are taking an object like this beam is there. This beam should be only acted upon by bending moment only. M or M plus dm. M plus dm. No shear force. SF is equal to 0. SF is equal to 0. Then only this is said to be having a pure bending or simple bending. Here I am setting. So here is said to be the stresses set up in the length of the beam are known as bending stresses. This total length is undergoing some stresses. Then it is called as flexural bending. And the relevant theory is called as theory of simple bending. So the theory which is telling about this all these things is called as theory of bending. So this is the second question. Okay. Next, third question, if you are taking here, define define what is a sectional modulus. So what is section modulus? Directly, it is given about Z is equal to I by Y max. So Z is equal to I by Y max. If I am not wrong, I will explain in my experience way. So if you are taking some beam, if this beam is having, okay, so what is I? It is a moment of inertia. Moment is equal to moment of inertia of any beam you can take. Now, what is this Y max? This is if you are taking a center axis, neutral axis. If you are taking from there, it is Y max will be there here. So Y max is this maximum Y by 2. Y max is equal to, if you are taking a beam, it is having Y by 2. So Z is equal to I by y max. So this is I is equal to, if you are taking a, it is the ratio of moment of inertia of section about the neutral axis only. So you are going to take a neutral axis. So neutral axis is there for a beam to the distance of outermost layer. So if I am taking a beam, if this beam is having, so this is a neutral axis here. So it is going from center to outward direction, from center to outward direction, center to outward direction, you can see. So all these layers in this beam, okay, they are undergoing some Z, what is that? Is section modulus. So this is Y max. So this is Y max, you can tell. So I by Y max. The distance of the neutral axis to the outermost layer is called as this one. So this is, I hope you understand this one. So fourth question I am taking here. Fourth question. Define the neutral axis of cross section. So what is neutral axis of a cross section? If you are taking this diagram now, if you are taking a beam diagram, this beam is having neutral axis here, NA. It is called as neutral axis here, N. Okay, so this is given by M by not a by. This is defined as a line of intersection of a neutral layer with the transverse section. It is transverse section. So it is a defined of line of intersection of a neutral axis. Nothing but the line which is at the neutral axis is called as neutral axis of this cross-sectional area. So this is the cross-sectional area at the middle. So write about the bending equation. So you have to write about a bending equation. So directly bending equation is given by I is equal to M by I is equal to sigma by Y into E by R. So here M by I is equal to sigma by Y into E by R, which is the simple bending moment here. So if I am not wrong, we will go into this one here. Definition is there. So here M is equal to bending moment. So M is equal to bending moment. I is equal to moment of inertia. So for example, rectangle BD square by 6 moment of inertia. Like that circle different hollow circle, hollow rectangle, rectangle. Both cases we are going to deal in this section. Sigma is equal to bending stresses here. Y is equal to distance of layer from the neutral axis. E is equal to Young's modulus of that material property. R is equal to radius of the curvature in order to calculate this bending moment equation. The sixth question, what are the assumptions of a theory of simple bending? This is the theory of bending. What a theory of bending says, that is, so theory of bending says that the material of the beam is perfectly homogeneous. What is the meaning of homogeneous? All same direction, and also isotropic. It should be the beam material is stressed within the elastic limit. What is simple bending saying is that bending of a rod is done within the elastic limit. You cannot go out of restriction. The value of the Young's modulus E, which is in the tension, in tension and compression only. So what is tension? If you are having a beam, if you are pulling them, it is called as tension. If you are having a beam, then if it is compressed, then it is called as a compression beam. The transfer section, which is where the plane before bending remains same after the bending also. So all this beam is there. The layers in the beam should be before bending and after bending same should be there. So this is the before bending remains same. So this is the explanation of equation of the simple bending, you can say here. So next question, if I am taking my seventh question, what is happening in the seventh question is, what is the moment of resistance? What is the moment of resistance means it is given by one word. The couple produced in a flexural member due to internal forces is called as moment of resistance. So it is a flexural member due to internal forces. Flexural stress itself is an internal force. Here, the internal forces is called moment of resistance here. So write the section modulus for the following sections. Rectangle section, hollow rectangle section, circular section, hollow rectangle section. You can see these four questions are very, very important in this. Directly it is given here. Rectangle section is given by, if I will draw, you are also unsure. If this is rectangle if this is rectangle is there, so Z is given by here BD square by 6. So it is given by BD square by 6 for rectangle section, that is equal to. For hollow rectangle, if this is a hollow rectangle, it is given by 1 by 6D is equal to big BD cube by small BD cube. So this is small b, small d So this is a big D here, which is there outside. So it is given by 1 by 6D times of BD cube minus BD cube, but big and small. Circular section. So if you are taking a circular section, if you are taking a circular section, what is happening? It is given by BD cube by 32. So if it is hollow, what will happen? Two circles will be there. So small BD cube by. So here it is given hollow circular section. Z is equal to pi by 32. Same. But big D minus small d cube. D power 4 big D power 4, small d power 4, D. So same only, these two are same, and these two are same. Only big D, small d comes in the difference here. I hope you are understanding all these ones for your good knowledge purpose. So next, if you are coming to ninth question, what do you mean by shear stress in the beam? So shear stress is already we have discussed from unit 1, unit 2, unit 3. Now in the unit 4 also, I am telling here shear stress is nothing but it is produced in a beam which is subjected to shear force is known as shear stress. So what is shear stress, Shear stress is nothing but only no bending force here. Only stress produced in a beam which is subjected to shear forces is known as shear stress tau. So what is the 10th question? What is the formula to find shear stress at a fiber in a section of beam? So formula he is asking for a shear stress. Tau is equal to FA y bar by IB. So what is this formula telling here is if you are going to take this formula this formula if you are going to take here what will happen is tau is equal to F to A y by IB. So F is equal to shear force in this one. So A is equal to area of the section. Y bar is equal to distance of the center of gravity of this one. And also I is equal to moment of inertia of the whole section. V is equal to actual width of the section. So you can see this is the all this one is shown here. Okay. What is the shear force? What is the shear stress distribution of the following sections? Rectangle section, circular section, triangle section. So if you are taking this, this is the general formula. You have to remember FA by IB. So if you are applying that one for rectangle section, circular section, rectangle section, here what is happening is you are getting rectangle section. Tau is equal to F by 2y into D square by 4 minus y square. So you have to remember this one. And also for circular section, you can see here tau is equal to what is happening, Tau is equal to F by 3i, F by 3i, F by 3i into r square minus y square. So directly you have to do the derivations, but here directly you can understand that it is derived and given for you here. That is f by 3i into r square into y square. So for rectangle section also, what is there? Tau is equal to f by rectangle triangle section f by tau is equal to f by 3i into xh minus x square. So it is given by derivation directly, but you remember here for 2 marks, which will be helpful for you in the examination. So then 12th question, if you are seeing, define shear stress distribution. Shear stress distribution. The shear stress, how a shear stress is distributed. The variations of the shear stress along the depth of the beam is called shear stress distribution. So what is the shear stress distribution here is 13th question, no? No, 12th question. The variation of shear stress on the depth of the beam. So only it is along the depth of the beam. So this is the beam if you are saying. So shear stress distribution is only it is followed upon this D only. We are only concentration D. Then only it is a shear stress distribution here given according to question. So next, what is happening? 13th question. What is the shear stress distribution for I section? So I section you have to derive. For I section, it is given by the shear stress distribution for I section is parabolic only. So I section, if you are taking, this is the I section. If you are taking I section is there. Okay, this I section it is a parabolic only. If this is a parabolic or I section, if you are taking this is I section is parabolic. But at the junction of Webuma, this is the junction of Web or flange. What will happen? The shear stress changes abruptly from F by 8I d square minus d to F by 8I into d square minus d2 into B by big B by small b, only big B by big B. So total this is I section, this is big B ma. For web it is a small b. So that difference is coming. Here it is given I is equal to moment of inertia, D is equal to overall depth of the section, B is equal to overall depth of the section, D is equal to depth of the web, B is equal to width of the web. So in this all the terms are related here only. Only difference is here only small b by big B because big B, I if you are taking I section, it is big B is for total section, but in the web it is small b is coming here. So remember this one very clearly. Okay. Next question is 14th question. Sketch the shear stress distribution for I section. So I section you can see this is the web neutral axis. So this is one line is coming. After that it is some parabola. After some parabola, it is again constant and constant and constant. So this is the shear stress for I section. So this is the big B. Okay, this is a big D. Okay, the web is there here. Web. This is the web. This I, this middle section is called as web. So sketch the shear stress. This is called as flange. It's called flange, and this is web. So again, flange web, flange web. Sketch the shear stress distribution for T section. So this is the T section here. In this T section, it is divided into tau max here, tau max here. So this is max. So this is a flange here, FLNJ flange. Then neutral axis and web is here. Web and flange is here. So the shear stress is given by here we have derived a derivation. It is like some D. This is the shear stress diagram for T and this is the shear stress for I section. Almost same, but some area is changed here. So with this we are ending the unit 3 and important questions here to increase our knowledge. Hope you will understand all these questions and they will be helpful for you in your studies and to upgrade your knowledge in the mechanics of solid in the mechanical engineering field. Thank you, ma. Thank you very much. Any suggestions, please you can give in the I will be uploading myself into next videos. Thank you.